Hi, all. So I'm going to go ahead and do some of the group work. I'm going to skip over what's not relevant for your exam that is just only going to be on the final because it's late and I'm tired, honestly. And I really felt like the other video that I already posted is much, much more helpful um, for the exam and synthesizing everything. But I did kind of want to show you how to apply it to some things. So if you haven't watched that video already, I honestly think that's going to be more helpful for you because I'm going to go faster on this than I am on that other one. That other one, I really went through like how the mechanisms form and why they do what they do and organized all the information. And here I'm just kind of going to fly through it. So the first question is to draw the enolate ion that's formed when it's treated with sodium ethoxide, so O minus. And you will get two possible ones if it is at room temperature. Or below, you'll get the kinetic product, which is the less substituted, less stable enolate, and it will look like this, O minus. And then if it's at an elevated temperature, you'll get the more stable thermodynamic product, which looks like this. And that's it. So this is the kinetic and this is the thermodynamic. This one, the enolate will form right here and the resonance structure on that will look like this. And there's not a thermodynamic or kinetic because this is symmetrical, so either side will be the same. And then on this one, there's not a thermodynamic or kinetic because there's not a hydrogen to steal from right here. So I went over this more in the other video, but for all these, your ethoxide is stealing a hydrogen, right? It'll steal it from here, or in this case, it stole it from here or this side. And so in this case, it's going to only be able to steal hydrogen from here because there's no hydrogens there. So you'll get this one. And this will be your two structures. Same thing here. There's not a hydrogen there, so you'll get this, and then, the arrows. This comes here, and this goes up. And so you get, no, I just drew the same one, this. And then last but not least, again, there's not a hydrogen to steal here. There's 1, 2, 3, 4 bonds already there, so the only product you can get will be this one. And it's in resonance like this. And I do want to I'm going to answer the second one all at the same time. So the second part of this question is predict whether or not a substantial amount of the starting ketone will be present at equilibrium. So this is just an acid-base question, and I talked about this in my earlier video as well, but your ketone plus a base is going to give you your enolate plus conjugate acid, so a protonated base. And you just are going to compare the acid and the conjugate acid, so the thing that gets deprotonated, the thing that gains the proton. So it has a proton, gets a proton. And you're going to compare those pKa's, and it's going to favor the side with the weaker pKa. So the pKa of a ketone, alpha hydrogen, is actually around 20. And the pKa of, in this case, our protonated ethoxide is 16 to 18. So actually the side of the reaction that's going to be favored is this side, so more ketone will be present at equilibrium than alcohol. Now, if we'd used LDA, that's pretty strong, and so its pKa is about 36. It's a stronger base, and so in that case, you'd favor your enolate and the protonated LDA, but in this case, actually, you favor the ethoxide and the ketone. Okay. Next question, draw the mechanism for the acid-catalyzed conversion of cyclohexanone into a tautomeric enol. So I did this one also in the other video, but I'll go through it pretty quickly. So basically, if you have a ketone in the presence of an acid, it's going to protonate. And then that leaves behind water. And because this is positively charged, electrons are being drawn up for that, making this even more acidic. So this can come, take this, and kick up. And that's how you get your enol. And there you go. Explain why only alpha protons are acidic. So I'll just use cyclohexanone. Those alpha protons, when you take a proton, you've left a lone pair behind. And when you leave that lone pair behind, if it can undergo a resonance, it will be stabilized. So in this case, if you take an alpha proton, it will be stabilized by resonance, and that actually makes it have a pKa of around 20. But if you took one of these over here, there's no way that this can engage in resonance. It'll have some inductive effect, so it probably would be closer to 45 than 50, or maybe closer to like 47, but it's still going to be very basic in the 50s. This is not going to be favored. So that's my explanation, is the electrons that are left behind when the proton would be abstracted by a base are stabilized, making it more willing to give up that proton, making it more acidic. Now, this next question is, which of these is more acidic? And actually, it's a very similar idea. So you have an alpha proton here that if you lose that proton, you'd have a lone pair, and it can undergo resonance stabilization. It can undergo that one time, but if you lose a proton here, it could undergo resonance stabilization on this side or on this side. So it actually has 2 times the amount of resonance structures. This would probably be, honestly, slightly more acidic than most alpha protons, because it has some of the inductive effect. So instead of 20, I'd probably put this as like 19 or 18, but this is going to be closer to like 10. So that's why this is more acidic. So the more ketones you have surrounding a carbon, like even if you had 3 ketones surrounding a carbon, then it would be even more acidic, right? Because you'd have 3 options for resonance, and this would be even the most acidic. So the more ketones you have around the carbon, the more acidic that alpha proton is going to be. You obviously can't have 4 because then there won't be a hydrogen there, but 3 is the max, and it's the most acidic. Okay, I'm not going to go through this mechanism. The purpose of this was really just to show you a different way to visualize the reaction, but everyone in the class did not like it, which makes me think you guys just like regular old mechanisms instead. And I did do a whole aldehyde condensation mechanism in my other video, but I'll do this one in particular just to get a little bit more practice. So because it's in heat, I'm going to go with the kinetic product and say that it will be deprotonated on the less stable side. And then it's going to attack its brethren over here and kick up. And it will make... So I've drawn this bond, and now the lone pair right here is what makes the bond between here and the carbonyl carbon of the other ketone. So it'd be O minus here. There is a methyl group on it, and then there's this isopropyl over on the side. So then this gets protonated. I guess it would be, most likely you had your sodium hydroxide, and it took this hydrogen here, and so it made water, and now this can steal a proton from that water. So really, technically, I guess it made water like this. So this proton came from over here originally, probably. So you'll get... Okay, so you get this structure, but ketones actually favor forming, especially in heat, the condensation product. And you could draw the condensation product where the base abstracts this hydrogen right here. This is the most correct way to draw it. And then this comes here, and this leaving group leaves. And then this would be your final product. Oh, that's gone. Sorry. Oh, no. Yeah, that's a methyl group. Sorry. Let me redraw that. That's why I should use pencils. something like this would be your condensation product. So you basically just lost the hydrogen and the alcohol. Sometimes I'll draw it where this OH comes and steals this proton, and then the electrons go here, and then the whole leaving group leaves at once as water, but whatever you want to do. So that's the mechanism for an aldol condensation. Not whatever it required us to do here, because y'all did not like that. And they always want to draw the isomer with the least steric strain. So because of that, I made it the E conformation, where the larger groups were opposite from each other. They're enemies. And the methyl group was on top, so there'd be less steric hindrance. So if you have an option, it's always going to go with the less steric hindrance. Okay, identify the kinetic and thermodynamic product. I like this question actually because it gives us practice on a few different things. So first, NaH is going to come and take a proton, and it can take one from here or from here. So either here or there. The one that's more substituted, more stable, that's the thermodynamic product. The one that is less substituted, less stable, that's the kinetic product. It usually forms at lower temperature. So both of these will form. And then actually this next step is just a substitution reaction. And this is also what we talked about as an alpha alkylation. So the alpha carbon is like, this is the main carbon, and one away is alpha. So the alpha alkylation happens just as an SN2. So this attacks and kicks this out, or this side attacks and kicks it out. Both of those will be able to do it. And then if you go here, you would get a benzyl substitution because it has a bend in it. Oh, and that's the thermodynamic, more substituted, more stable. And then the kinetic is the less substituted, less stable. That's my terrible benzene. There you go. Okay, this next question, which of the following would be considered a stabilized enolate and why? This is actually the same as what we talked about earlier. So if you got an enolate, it could take at the alpha position. And in this case and in this case, there's two resonance options, but in this case, there's only one. There you can't get resonance from all the way over here. So this is stabilized by two resonance situations, so it's an extra stabilized enolate than a regular enolate. And again, if there were three, then it would be even better. So like if you had this structure, I don't know how the structure would exist. It would be chaos, but if you had it, this one right here would be an even more stabilized enolate, and that proton could get abstracted, and it would leave a lone pair behind that would be really stable. Okay. I'm not going to talk about Michael additions because it's not on your exam, and I am going to bed. So I'm going to leave this for later. And I'm going to jump down here because these are fair game for your exam. This one had a correction. There should be a BR2 on there. And these are all things that we also went over in the video I talked about. So this is acid catalyzed bromination. So acid plus bromine is going to give you a bromine at the alpha position. And then we add a base to it. So this is just an elimination reaction. So you should get something like this hydrogen gets taken by the pyridine, and these get left behind. And that's a good chance for you to review E2 reactions. This one is the special reaction. It's like a HVZ, Helsen, I don't know, some German name. The first step, PBr3 with the Br2 will actually fix your carboxylic acid to be brominated. And then when you add that to Br2 at the alpha position, it will brominate as well. So you get a bromine right here. And then you can add water to go like this. And one thing I like about this reaction is in your notes, it was like, the proposed mechanism is this. It's believed to go by this mechanism, which is fun because I think that means they don't actually know. And I like it when I think it's really nice for us as scientists to remember that maybe we don't exactly know everything. And a lot of times we're just like giving our best making our best guess, I guess, but a really well-educated, like based on all the evidence we have, this is the most plausible solution. So I just like that. This is Br2 with NaOH can do a base catalyzed alpha bromination, so adding bromine at the alpha position, but actually it can do that multiple times. I'm not going to go through the mechanism because I did it in that other video, but it can do that 1, 2, up to 3 times. And then the NaOH can come and attack actually, and it would, do its thing where it attacks at the nucleophilic center. And the reason it would do that is because or at the electrophilic center, sorry. It's so electrophilic because these bromines are all electron withdrawing and this oxygen is moving those electrons up there. It's got that resonance structure. So it will attack and be an OH here with carbon with 3 bromines on it. And then this can come back down, and this is actually a good leaving group because it has all those bromines, and you'll get a carboxylic acid plus CBr3 minus. The minus charge is actually on the carbon, but then you add acid, and it makes it HCBr3. And this is called bromoform. You've probably heard of chloroform, CCl3 with a hydrogen, and there's also iodoform. So all these are formed the same way. If you have that halogen with the hydroxide, it will just like repeatedly attack over and over after the enolate forms. The first step, I guess I should say, is the enolate forms with the NaOH, and then it attacks the bromine, and that's how that first one gets going. But yeah. Okay, so this next one, I think this sometimes throws students off on exams. So you might see this and you're like, oh, with base and a ketone or an aldehyde, it's going to make our enolate. And then you might be like, now what? Like, what is it going to attack? There's nothing for it to attack. There's no electrophile. It can't do an SN2 reaction. There's no halogen. Whenever you feel that way, that usually means that it's a condensation reaction and it can react with itself. So that actually is what's happening here. So, it's actually going to attack itself. And you'll notice I like to draw the ketones near each other because it's easier for me to visualize. It also is really helpful at this stage to number your carbons. So 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. And actually the bond forms right here between carbon 4 and then our O minus. So we'll make that carbon. I'm going to not make this 5 anymore. I'll make that 5, 6, 7, 8, 9, 4, 5, 6, 7, 8, 9. Okay, so this is an aldol condensation where an aldehyde or a ketone gets deprotonated and it reacts with itself. And then the initial step, this sodium hydroxide stole this proton, which means you have water floating around. And this will actually steal that and become alcohol. And it can go one step further and become the condensation product, which would look like this. OH. One, 2, 3, 4, 5, 6, 7, 8, 9. It's kind of a weird structure, but that's the basic idea. Probably would have been better for me to actually draw this one attacking this one, but what can you do? So that is your final reaction there. And this is also an aldol condensation, but it's a crossed. So it's reacting with this one, but it's actually not a super messy crossed aldol condensation because there's only one alpha hydrogen that can be abstracted. So you can take this and it'll deprotonate with the NaOH, so that becomes water, and this is your enolate, and it attacks. And then you get this structure. This forms the bond to right here, O minus, and then you have an H and an H. That'll get protonated. There's not enough room on this paper. That'll get protonated to be OH. And then it can do an elimination. Actually, I don't know that it will, because if it did an elimination, oh, that's why I drew this wrong. It actually is like this. There's 1, 2, and then the OH. And then it could do an elimination to look like this. There you go. So that's a crossed aldol condensation between two different ones. And then it looks like down here we have a self-aldol condensation where one side will become deprotonated, and then it'll attack here and kick up. And again, this is where it really helps to number carbon. So I'm going to say 1, 2, 3, 4, and it attacks on 5. So I'm going to go ahead and make a 5-membered ring. 1, 2, 3, 4, 5. So 2 has a ketone on it. 1 bonded to 5, and then 5 kicked up and became an OH. So that's a 5-membered ring. I don't know if the condensation product would be favored, honestly, here. I mean, it says heat, so maybe then it would just be like this. Oh, I think I made a mistake. There's also on this where it attaches, there's a methyl on carbon 5. There's also a methyl group. I left that methyl group off. My bad. There you go. All right. And then this last one, I think this sort of does the same thing to students where they're like, okay, NaOT, that's our base. And when there's an ester, you want to use the alkoxide or like the deprotonated alcohol that matches this R group right here. So like OET, you're going to use OET minus, or if it was a methyl group, you'd use O-methyl so that it didn't change out the ester. But so it'll deprotonate here, and you get this. And students, I think a lot of times are then like, now what? There's nothing for this base to react with. Is it just going to get this acid and reprotonate? Whenever you get to that point, assume that it's going to react with itself. So it's going to react with another ester. And remember, Claisen condensation, the mechanism is very similar to aldol condensation, but the leaving group that leaves is what's different. So this is going to come and attack here and kick up, and you'll get OET, and that will be bonded to, oh, I did not leave myself enough room. I'm going to go down here and draw it, because I did not leave myself enough room. There's not enough room on this page. OET, and then up here, what it bonded to is okay. So it came and attacked here and kicked this up. So it's bonded to an O minus with an OET and, oh wait, no. I guess that was directly attached. That can be your benzene, doot doot. And then over here is an OET. That was hard to draw. Hopefully you guys followed. This is where numbering your carbons again comes in handy, but this can come down and kick out this leaving group, and you get, I'll start with the blue again. OET. And then your benzene ring, and, oh no, I do that wrong. Ugh, yeah, my late nightness is showing. See, even when I don't number my carbons, I pay for it. Okay, OET, and then that's bonded to a ketone, which is bonded to a benzene ring. Boom, there we go. Okay, because this came back down, kicked this out, but everything else is the same here. Okay, so, and then actually the OET that got kicked out, this one right here, is going to come and deprotonate the alpha hydrogen right here. That's really, really acidic. It would deprotonate that, and because of that, that's why we have to add the acid as our second step. And then it'll restore to this. So that's a Claisen condensation. The addition part, again, is exactly the same as an aldol condensation, but when it kicks out the leaving group, that's where the difference gets made. Okay. Now this next one, part of this, I think is slightly outside the scope of your next exam, because I don't think you did all of the melodic ester stuff, but we'll go ahead and do it. So the first step is you get this lone pair that forms right here. Your NaOET will come deprotonate, and then you'll have ethanol in the solution. And then it's just going to do an SN2 reaction, right? It's just going to come here, kick this out, and you've actually just alkylated that, ET. OET, OET, and then you have your benzyl group, and then we do it again. NaOET is going to then deprotonate that, and then we actually have another SN2 reaction. So ETO, OET, and now you have your benzyl group over here. And over here you added 1, 2, 3. Let's see, 1, 2, 3, 1, 2, 3. Pentane group, and then this H3O plus and heat will actually turn this, it's kind of a weird reaction, but it'll turn this into an OH, and then the water will leave, and so this just turns into a carbon. Or actually the CO2 will leave, I think. And this just turns, like, this is just becomes like the hydrogen bonded right here. And so what you end up looks like this. I don't think that's going to be on your exam tomorrow, so I would not worry a ton about that, but it's called a decarboxylation reaction. And we have not talked about it extensively, so if that's weird to you, that's okay. Don't worry about it. Okay, and then these are some from previous chapters. So this is a Wittig reaction. I'm not going to do the whole mechanism because I've done that in the past, but basically I will line up the O and the P, and then these two things bond to each other and these two things bond to each other. So you'll get I can't remember when it makes E or Z, but you'll get this or the isomer of it. I think it's probably the isomer. And then this is a Bayer-Villiger. So the migratory aptitude for this is it will move H first, then a phenyl group, and then it's more substituted to less substituted. So this side is a quaternary, this side is a tertiary, so it's going to go on this side. So, and it's important to remember, it doesn't break, like it doesn't substitute, it literally adds a new bond in. So let's see, 1, 2, 3, 4, 5, 6. So 3, this is 2 now. 1, 2, 3, 4, 5, 6. So that was a 5-membered ring, and I just numbered the oxygen like it was 6. So 1 has the ketone and 6 has the methyl. So it'll end up looking like that. So just added the oxygen in. This is a Grignard with CO2 that makes carboxylic acid. You actually did that reaction in your lab where you should have, where you did a Grignard and you poured it over dry ice and then you acidified it and it made white precipitate. So there you go. Dibol will turn this ester into an aldehyde, but it actually, the leaving group leaves, right? So when the leaving group leaves, the hydrogen from the dibol comes, it attacks. This comes back down, kicks out the leaving group. The leaving group leaves, but the leaving group is still attached on the other side. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7 on the alcohol. So this is what you'll get. Very similar to what we had on the last quiz. And then LAH here. This is secondary, so it can only oxidize it to a secondary alcohol. So it should be that. Propose a synthesis for the following reaction. Okay, let's look. So to get a primary alcohol to an aldehyde, you need PCC. So I think I would do PCC to start with. Ooh, I know what I would do. So that gets us to an aldehyde. We don't have to add anything. All we have to do is make a double bond right here, right, after we've gotten to our aldehyde. And so we learned that if you add a bromine here, then you can use pyridine to eliminate it. So I think to go from here to there, I would use PCC to get the aldehyde. And PCC would indeed give you the aldehyde. I don't know why I drew that so weird. And then I think I would do H plus or H3O plus and Br2 to get an acid-catalyzed addition of bromine at the alpha carbon. And then I would use pyridine or tert-butoxide in heat and do an elimination reaction. Tert-butoxide might be too bulky, but yeah, that's how I would do it. So there you go. Is that everything? Oh, and then it's just a review. So I hope that was helpful for you. If you have any questions for me, feel free to reach out. And good luck studying for your exam tomorrow.